All right, welcome to Embedded Systems. We are in, ooh, I should show this slide, this is always good. Systems. This is lecture 24. And of course, we're talking about operating systems, or just the general concept of operating systems. So here's a good question. How many of you have had actual entire classes or an entire class in operating systems? Okay. How many of you have had at least one lecture on operating systems? Ooh, this is even scarier. Okay. What is an operating system? So I guess that's the first question is, what is an operating system? Shout it out. All right, who's not going to say? I'm going to start calling people if nobody makes a suggestion.
Windows.
All right, here we go. Windows. Apple OS. Isn't that iOS? Next. Linux. I can't hear anybody. Somebody say something else?
Raspberry VC.
I can't hear you.
VC Raspberry. That we put it on the Raspberry.
Oh, is that a variant? That's a Linux variant, isn't it?
Its name is VC Raspberry.
Is it based on Linux? I think.
Yes, it is.
Yeah, so it's Linux. I mean, just like Windows. All right, here we go. DOS. You're gonna have all that, right? So all of these. Oh, by the way, and there are a whole bunch of proprietary ones. Android. I'll go for that one. For that matter, there's also Windows embedded. CPM, that's an old one. All right, so good enough. Remember, the camera can pick you guys up if you want. What you say? So when you think of all this, what's the first thing that comes to mind about the amount of software? Is there a lot of software associated with an operating system?
Yes.
All right. Typically, you're going to see bloat. Back in the old days, on something like some sort of old crusty Seafair or something like that, the disk operating system that came with your typical PC would boot from a floppy disk. 160 kilobytes of memory, and it didn't even take that much. Nowadays, because of all the graphical user interfaces, there's a whole bunch of other things going on. Really often you'll see operating systems expand to the size of memory available. Because don't forget, in the original PCs, the 1981 PC, even though it had a capacity of 640 kilobytes of memory that you could have in memory, or RAM that you could have, an address in memory, that's all you got. So you didn't fill up everything with your operating system, and in fact, it ran something called BIOS. So it had its own bootable input-output system space that was anywhere between, I think it was begin with, I'm not positive on this, I think it was 32K and it finally expanded into 64K. And that handled most of the operating system interfaces with hardware. Then you had file systems and you had other aspects parts of that too. So typically an operating system, back in the old days, were somewhere between 32 and 64K. The rest of the space was allocated for the actual application, not multiple applications, but the single application that ran. So what has changed between the original PC DOS to nowadays to Windows or anything like that? Okay, I kind of alluded to that already, right? So back in the old days, what did I say there was running on your machine? So what was running? The OS and one application. So now what's running on Windows and Linux?
Anything you want.
The OS and N applications, right? You could run all sorts of stuff at the same time. So back in the old days, the operating system and one application, one service. And now, if you were to look at the task manager under Windows, you would see, I don't know, anywhere between 50 and 150, 200 services running. There seems to be a whole bunch of stuff running. Now, step back and say, and think of embedded systems. What do embedded systems more closely replicate between these two? Or what do they look more like? Do they look more like DOS? Or do they look more like Linux? Or does it depend? It depends, right? So this basically is a Windows, Linux, iOS. It is a full-fledged operating system with lots of memory. Lots of memory. All right? However, if you look at this, and here, just that embedded system, very, 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 very low level. I can guarantee you Linux is not running on this. I can probably guarantee you that DOS is not running on this. In fact, some of the most simple machines don't have anything more than a simple while loop running. And that's their operating system. That's often what they call roll their own, very, very low level. So what does an operating system give to you? So think about it. What do you use? So what does an OS do for you, other than give you headaches? I've already mentioned a couple already. See if you pick that up.
Memory management.
All right, now people talking. All right, say it louder.
More usage or more applications.
All right, ability to run more than one application. So I can call this maybe multi-threaded. All right, what else does an operating system do for you? Oh, somebody had it over there. What did you say? No? Oh, come on, think about this. What do you use on your PC, on your Linux box? Did you say crap? Graphics, all right? It gives you the ability to several, or I should say, access to several hardware devices, i.e., Oops, I was gonna spell graphics wrong. Graphics display. Keyboard. What else does it do for you? Say that again, louder?
Trash collection.
Ooh, let's see. It, I'll call it manages RAM on machine. So it allows you to allocate temp spare storage, right? It allows you to release. This is a big one that nobody has addressed yet.
Consists drivers
All right, drivers. Drivers for what?
for the peripherals.
Let's see. So I will call this
Device navigation.
simple and consistent interface. That's not an interface, that's an interface to hardware. And I will call this drivers. I'll just do this since nobody's ready for it. This be a file system. These are some of the major things that an operating system will do for you. Now, the motivation of this versus a simple OS. So if you have a simple OS, or you have a simple embedded device, is probably better to say. If you have a really simple device, are you going to have a lot of pieces of hardware hanging off of it? Maybe not. Are you going to have a lot of applications running at the same time? Usually not. Are you going to have a complicated file system with lots of levels of storage? Usually not, all right? Oh, by the way, file system, I should also say a memory management unit, and that goes a little bit beyond manages RAM. You are familiar with the concept of running a program, right? The executable program comes in from a hard drive, usually, into RAM memory, and then it runs from RAM memory. Does that program exist in two places at the same time? Yeah, it's still on the hard drive, and it's in RAM. Now imagine this. Let's say you have data on the hard drive, and you want to use it, and it is brought into memory. Does that data exist in two places? All right? Now, programs usually don't change. So when you bring a program into RAM, that's not going to change. When you bring data in, could it change? Yes. So now you need some sort of operating system control of saying, okay, if this has changed, I need to make sure that the hard drive space will be updated when I'm done using it in my memory space. So you need something that will be what we call a memory management unit that will take care of that. So if you have a simple embedded device, you'll not need most of these functions. Now, unfortunately for this class, we're getting towards the end of the semester, so we're not going to be able to go into great detail about operating systems. But we will visit this in our advanced embedded course, and for those of you who are thinking about it, real-time operating system is going to go into it from a Linux standpoint. I'm going to go into it from a roll-your-own standpoint. I may even have a micro OS. We'll see just how tiny we can get these operating systems. So, now that I've given you some motivation and some ideas of why we do some of the things that we do, I want to start talking about sharing the processor. In other words, what is important about supporting concurrency. So let's take a look at all of the functionality. By the way, there are some references for this. And the one thing I do want you to think about is you have to find what the best fit is for an operating system depending on the complexity or the expected complexity of your device, all the resources that you have to control, energy available for that, etc. But what I'm going to do is I'm going to give you a basic description of operating system, and then thereafter we will take a look at some examples of concepts that need to be implemented in software to get an operating system to run. So, from that respect, no shoe fits all. I like these big shoes right here. Those are my favorite. So, there are several questions that you will have as to what level do you have your operating system and what support. For example, I talked about the simple while loop. That is literally your simplest operating system. And in that case, usually if you have very simple peripherals that you're working with directly through the microcontroller, that's good enough. As long as you have the ability for interrupts, that usually works out well. However, you can go all the way up to a full-blown real-time operating system based on Linux, based on Wind River is one proprietary company that does this. Could be Windows embedded. I went to a workshop where they handed us a little robot and said, okay, you're going to program this in Windows embedded. It's just so easy. And actually it was pretty easy. And then they started adding lots of stuff to it and it got loaded again. So let's think about what we're going to be doing with an operating system. How do you schedule the tasks in the CPU? Remember we talked there may be several things running at the same time. It's important to know which one runs. Because as it works out, if you have one processor, one central processing unit, literally only one thing can execute at one time. If you have a multi-core, 4 cores, still only one thing, only one program can operate on each one. So if you have many hundreds of services running, only one can run at a time. And so you have to determine when do you give time to something. When do you run Microsoft Windows on your operating system, and you let the Microsoft Outlook with the timer run in the background. And then when do you say you're paused Microsoft window, and Microsoft Outlook will come in and it will run and maybe set off a timer or something. So you have to look at the respective operating system, real-time operating system. What are you going to, or how are you going to play fair so that everybody has a chance? So, here are some basic definitions I do want to cover in this class, and that is, there will be what I will call a process, or a task, or a thread, and I may use those interchangeably because it depends on the operating system, the person, the book, whatever. Sometimes they're used interchangeably. But imagine this. At any one time, there may be many of these things, many of these tasks, threads, whatever, ready to run. Let's look at one example. Let's say you are communicating via RS-232 on your embedded board. And then also let's assume that you will want to have a timer running and have the timer operate. And maybe you want to receive RS-232 data. So you have many things that may want to operate at the same time. So you have to identify the time at which some task is ready to run. It may not run currently, but it's ready to run. Then there is the response time and the delay between when that task is ready and between when the service is done. There's going to be some latency time associated with between when it is ready and when it actually starts to run. There's also the time associated to perform that task and the time for ISR, maybe a time needed to run a specific interrupt service routine. Now, one thing I want to point out is there are several things going on in this display. Notice that we have some non-critical task running right here. Then there is something here called scheduler. This would be a operating system function. The operating system function is not real work that has to be executed, but it's there to allow different other tasks to run to be fair. So as you can imagine, would it be good to switch really frequently between tasks that need to run? I mean, like really frequently. Well, if you have a certain amount of scheduler time that needs to run every time you do what's called context switching, whether you switch from this process to an ISR, if there's always some overhead associated with that, obviously you want to reduce the amount of overhead that the scheduler takes. This is the amount of time that it's saving some registers, that it's saving some data, because you're going to change what's running inside the machine. So you want to reduce this frequency, but then you also want to be fair to allow this enough time to run. And something else to start running if it's really important. So there's a nice trade-off that you're going to have to learn how to do. So here is a simple example of one operating system construct, and it's called round robin or Superglue. And it's simply a, okay, what does this say right here? What does this mean? If I have this while loop here, and it says true, what does that mean? That's the while one loop, right? Do this forever. The basis of any embedded system. All it's doing is it's polling. Device A, do you have anything to do? If you do, then I'll give you some time until you're done. The important thing is it's until it's done. There's no interrupts. You don't share data between anything else. And if something takes a very long time to run, it takes a very long time to run, and it doesn't share. Then you ask B, then you ask C, and then you go back up to A. And the nice thing about this is everybody gets a share of the processor. It may be rather delayed, and there's no priority whatsoever in this. So is this a good one to use? I don't know. Let's look at an example. So, we could have this example in a handheld oscilloscope or a digital multimeter. So based on the switch position right here, in the case of ohm meter, we're going to do this, then this, then this, then this, and this, and then when we're done, we're going to go up and do it all over again. Or in the case of, you turn it over to the volt setting. So in this case, the switch really looks like it's only going to do one thing at a time, but that's not a problem, is it? Because we're basing our super loop, or our round robin application, on a setting right here of this switch. And this switch can only be set on one thing at a time. So if you have it on this setting, over here, which might be ohms, and then you switch it over here to voltage, well, it's going to finish up the ohms one, and then it will go back and check for the next one, which will be voltage. So that's not a big problem in that case. And on top of that, then we display everything, and then we delay 50 milliseconds. Now, the motivation of why this would not be good is as follows. Let's say we have also, let's see if I can set up this problem. Okay. So let's say we have this problem. There are these different things that go on. That's interesting. We're going to work with video and audio. And just looking at this, what takes more time to do, video or audio? Video, obviously. What happens and needs to be processed more frequently? Well, here it says 20 milliseconds, right? So that needs to be done more frequently than this one up here, which is 33.3 milliseconds. Can you do everything in the time frame needed to execute? In other words, do you think that if you had a processor like this, where you say, in my Superglue, if it's time to sample, we're going to sample the frame, compress the frame, and send the frame. Do you think that we would ever have a time where you need to handle audio, and audio just does not get any time? So let's see if we have an example of this. So if we have a situation where we need to sample the audio, and then compress it, and then send it. Hold on, wait. This is the video up here, and then this is the audio. What happens if this compressed frame actually runs at any time that you need to handle this audio? It could easily happen that you will miss. Because this has a 20 millisecond deadline, you will miss this right here. Because you're in the middle and you say you start this function and you don't interrupt it and it has to finish, you can obviously miss this deadline of 20 milliseconds for all of these tasks, even though they take only a small amount of time. And it looks like it would be fair that if this only has a little bit amount of time that it needs to be done, wouldn't it be more fair that somewhere in the process of doing this computing, you would be able to say, oh, wait a second, I've got to do only this small amount of audio right here, and then when I'm done, I can go back up here to the compressed frame. So remember, we've talked about interrupts, right? This would be an excellent opportunity for an interrupt to occur. Now, let's take a look at this. How much time does this all take? So let's add this all up, right? We're talking in these milliseconds, 161, 162, 163, 32, 3, 32, 4. So this takes 3 to 4 milliseconds, right? So 3 to 4 milliseconds is definitely enough time if we had everything going up here. How much does all this time up here take? Let's see, 27, 28, 29, 30, 31. So that looks to be about 31 milliseconds up here. So if we, in the process of this, all of this video stuff running, then we stop for a moment and handle this, which takes less than 1 millisecond, right? And then it goes back and executes this. Will we ever miss a video deadline? Not really, right? Because even if we do 2 of these, remember, there's a possibility, since this happens every 20 milliseconds, even if we do 2 of these in this time frame, this is only going to be 0.65 milliseconds. Definitely an amount of time you'll be able to make this deadline without any problem at all. So maybe we need to think about, this round-robin Superglue might not be the best application or best operating system for an application like this. So this pretty much says what I did, except we use math. So again, the voice recorder, sampling the microphone, 15 hertz, updated 4 hertz, will you be able to do it? So it just pretty much describes the problem that we have. So I guess maybe we should use something that's more event triggered, using interrupts. So let's take a look at this example. Does anybody ride a bike in here? No? No bikers? One? Bikers or cyclists? What are you? You're cyclists. Like bikers wear leather and they have big, huge Harleys, right? Do you have a Harley? I figured you had a Harley. No. No Harley? Okay. Is that a nice one? It's not one of them little midget things, right? No. All right. So, yeah, again, this is again for is you have a question up there, or are you just stretching? Oh, you're stretching, right?
Yeah, I'm stretching.
Okay. So here is a basic architecture for a low-power device. Very little code, very little time overhead. Everything is going to be based on interrupts. And that's because what happens on this bike computer? A bike computer will actually be able to identify how far you're going, and it'll keep a clock up, and it will have a liquid crystal display, and it'll actually have a button that you can change some stuff and do some programming on it. So what are our interrupts based on? Well, when it's running, wheel rotation. So every time the wheel passes, it says, oh, I now have gone a certain distance. Haven't we gone over in this class about how far that would be, circumference of wheels and stuff like that? Or am I thinking of my Intro to Engineering class, right? Oh, I just did it a couple of weeks ago. So yeah, if you have this wheel, and how big is your typical wheel? Is it 21, 24? Let's say it's 24 inches in diameter, right? So if we put a sensor right here, and we put our little computer here that is looking for that sensor on the wheel, it's not attached to the wheel, right? When this goes around one revolution, how far has the entire vehicle traveled? In other words, what's the circumference of that wheel? And it is 2 r pi, or 2 pi r. So, oh good, somebody did the math. Approximately 75 inches, which, if we're really good at our math, is a little bit more than 2 yards, or 6 feet, and actually it's close to a meter. Even though a meter is 39, so it's not going to be quite that far. It's close. It's a little bit less than 2 meters. And then it would want to, and that will generate an interrupt, right? We already know what an interrupt is. Whenever we start pushing buttons, yeah, that's another interrupt. And oh, we're going to have this little real-time clock inside. And the neat thing about this is that when you have a device like that that is based on interrupts, if nothing happens, like If it's sitting in your garage, it's gonna do hardly any amount of consumption of the battery. It's just like your watch, right? This thing has been running on a watch battery for at least 4 years. Same battery. It's hardly doing anything. Excuse me, I don't push the light button much, which is what uses it up. The clock uses hardly any energy at all. So from that perspective, then everything could be based on a simple while loop that puts it to sleep. And all the computation is done in an interrupt. So what is it? Well, whenever the wheel rotates, we're going to increment that. And then we're going to do some computation about how far we've traveled. And we'll do some computation on the speed. And then we will actually return from the interrupt. And actually it says nothing in here about updating it on your display, right? So maybe it doesn't even do that. So here's a mode key, and then we're going to do some functions on that. And then here is the time of day timer. So it looks at least here, it's going to be doing some computation. So once the timer ticks, oh, look here. It only updates the LCD based on the timer tick. Well, that makes sense, because if you're computing miles per hour or something like that, would it be better to kind of base that on time, right? So when the timer tick happens, then it will do computation of how far it's traveled. It'll actually refresh the LCD and do some displaying of your speed on it. So that looks like a neat example, right? Do I need a nice, really complex operating system for this? So this is an example very similar to your watch, where you really don't need an operating system. Usually hardware can handle this because you're using interrupts. And in fact, in this case, you probably don't need anything other than a while loop. But there are limitations. So all computing must be triggered by an event, so you're spending a lot of time in your interrupt service routines. Typically, you have a limited number of timers on your microcontroller. So you might actually have to allocate those timers in a different way. And then everything is an ISR. Usually you don't want your ISRs to be very long. For example, it might be more worthwhile to only have in your ISR a little bit of activity, and then when it gets out of the ISR, instead of sleeping here, it'll see if it has to do any work, and if there is some work to do, then it'll start to work in the loop. All right. Oh man. So, let's see how far I'm going to go on this one. Looks like I have a lot of slides to do on this. So what I want you to do is to go back and make sure you read chapter 12 in the book and take a look at the notes that are going to be posted. And I will address these in great detail in our next class. Thank you very much.